Hi Algebra 2B students, how you doing today? Welcome to our video on 7-6, the natural base. So, our objective today is to write, graph, use exponential and logarithmic functions with a base of e. So you have been used to using base of 2, 3, 4, 5, very common, and a base of 10, which actually is the common base, right? On our calculator, here's our log, L-O-G, with a base of 10. Today we're going to be looking at ln, the button right below, which is the natural log. So ln stands for like log au naturel. Notice above it in blue, it has a base of e. That's right, you really can have a base of e. But e isn't a letter. E is actually a number. I want to show you on the calculator also that there's an E above the division button, okay? And so I'm just going to put the calculator aside for a moment so that you can get these notes down. And we talked about the lesson objectives, and then the natural logarithm then is a log with a base of E, shown as ln, and it says C on calculator, and I already showed you that. So one more time, and we will be using it. The natural log, when you see ln, you won't see a little base to the right and below it, but because it's ln, you'll know it's an e. Just like when you see an log without a base, you know it's a 10. So number 2, the natural logarithmic function is ln of x. This you can graph also on a y equals screen. You can use the natural log button to solve problems. It is the inverse of e to the x. Okay, so what is e? Let's hit that button on the calculator. If you need to pause to take these notes, go ahead. But let's get e on the calculator. Let's look above the division button here, and because the e is blue, we can do second division. And notice that e is a real number. It's 2.71828 repeating, just like pi is a number. You can also get e above the ln button on the left. So if you hit the natural log, sorry about that, I meant to say if you hit this blue button, the second button, and then natural log, it shows the e, and I just want e to the first power, right? That's e, and there you go. There's 2.71828 repeating. Now, what is e? So it turns out when things, natural things, grow, little bits of growth over long periods of time, just like trees do, grass, just like you did or are for a portion of your life. It turns out that there's a natural base E that helps show natural growth. Same with natural decay, right? If you have some vegetation outside that's decaying or minerals, there's lots of bases that show decay. But natural decay uses a base of E. It is the base that best shows little bits of growth or decay over long periods of time, like the world works. So you are very used to a base of 2, right? A base of 3, base of 4, base of 10. E is a real base. It's not a variable. And so because e can be the base of an exponential function, and it can be a log with a base of e, again shown as ln. This means that all the rules of exponents apply to a base of e, and all the properties of logarithms also apply to the natural log. Let's fill in the chart below. So when you have a common logarithm, this is a base of 10, and here's natural logarithms with a base of e. Right? So the base for a common logarithm is 10. We're going to go straight down. It's a logarithmic form. Let's just do an example. Log of 100 equals 2. That's using a base of 10. Its exponential form, would be 10 squared equals 100. Notice here that this would be then for the common log, right? This would be log of 1, because you know that your base is 10, and we usually don't show it, you're welcome to, and we know that is a 0, right? Because when the base is 10, what's the exponent? When the base is 10, the exponent is 0, and the solution is 1. Let's take a look here. We're going to fill in 10 for the bases. Log base 10 of 10, right? That is a 1. The properties apply too. If you have log with a base 10 to the x, then the log base 10 and the base of 10 cancel and leave you with an x. Also, if you start with a base of 10 and your exponent is log of x, also base of 10 when we don't show it, a base of 10 and a log base 10 cancel out and leave you an x. Let's see how the same process works for natural logs. So for natural logs, it's just that the base is e, which is 2.71828, and it repeats. Logarithmic form then would be the natural log of 100 equals, and I'm going to get that from my calculator. Since it's not quite as easy as a base of 10, we get a decimal. Natural log of 100, let's go to the third place, the thousands place, 4.605. There we go, there's logarithmic form. Exponential form, let's do e to the 4.605 will equal about 100, right? The inverse of the line above. Let's do the natural log of 1. Again, that means there's a base of e here. You're welcome to use your calculator, but we know if you have a base of e and the solution is 1, the exponent must have been 0. Same rules apply. Let's do the natural log for the b and the b. Let's fill in an e. Here we go. So again, the base is e, the solution is e, so the exponent must be 1. When you have a base of e and an exponent of 1, the solution is e. So notice then that when you have the natural log of e, of course, with a base of e to the x, that these cancel out. The natural log base e with a base of e leaves you an x. Or if you start with a base of e and your exponent has a natural log of x, the e cancels out the log of e and you get an x. So all the same rules apply. Okay, let's go to the next page. Now, the natural log of e is 1. So important. Let's check it on the calculator. The natural log of e. Sure enough is 1. This makes perfect sense because when you have a base of e and the exponent is 1, you get an e. How does this help us? Well, 1 cancels out 1 times anything, leaves you with anything. And so oftentimes we don't even need that 1, it cancels. So let's take a look on 1, 2, 3, and 4. Because we have natural logarithms, we can apply all the properties that we know of logs. So the first 4 are going to be the power rule. Let's take a look to see what they did. They said when you have a log with a base with an exponent on it, by the power rule, you can bring the exponent out front and multiply it by the rest of the log. Now notice the natural log of e is 1, so you're just left with a 6x. If we had to solve for x, we made a really easy expression. Again, when you have a log and the solution has its own exponent, by the power rule, you can bring it out front and multiply it by the rest of the log. The natural log of e is 1, and we are just left with t minus 3. Isn't that awesome? take a look here on number 3, little extra going on. We have to have the base of e and the natural log right next to each other to be able to cancel them out, and we can't. There's this 2 in the way. So, because the 2 is multiplying the natural log, we're going to use the power rule to bring that 2 back up and make it the exponent on the x. So the expression I'm pointing at and the one below are exactly the same. Now, a base of e and a natural log with a base of e cancels out and leaves an x squared. Kind of fun and easy. Number 4, the natural log of e to 1.8. I can bring the 1.8 out front by the power rule, multiply it by the rest of the log. The natural log of e is 1. You are left with 1.8. The product property and the quotient property also work with the natural log base because they are properties of logarithms. So let's do some math here. Notice we're trying to solve for x. We have the natural log of x plus the natural log of 4 equals 2. Notice that because of the plus sign here, that we can use the product property. We can write 1 log with the x times the 4. And I will write that in this order, 4x. The natural log of 4x equals 2. So by the product property, this expression on the left equals this expression on the left. Now to solve this problem, I'm going to write it exponentially. Remember the base is e. So I'm going to write the exponential problem. When the base is e and the exponent is 2, remember the natural log is an exponent, the answer is 4x. All right, let's get e squared from our calculator. Here we go. I'm going to use second natural log, and there's my e squared. We'll write it to the second place. 7.389. 7.389 equals 4x. And now we can just divide both sides by 4, and we get x equals 1.847. So we're going to find a lot of our answers have decimals because we don't have those nice bases of 2, 3, 4, 10. E is 2.71828 repeating, so it causes a lot of decimals. Let's look at the quotient property. We have natural log of x minus natural log of 10 equals 3. I need just 1 natural log to solve this problem more easily. With the minus sign, I can see this is the quotient rule. So I'm going to write 1 natural log of x divided by 10 equals 3. Okay, I'm going to write this problem exponentially so I can solve it better. We know the base is e. Here we go. That would be e is the base, the exponent is 3, and that equals x over 10. Now, I could get e cubed from the calculator, or I could wait a moment. To solve for x, I can multiply both sides by 10. There we go. And my x equals 10 times e cubed. Let's get that number. 10 times e cubed. 200.855. There we go. And let's see, do we have another page? We do. Okay, I wasn't sure. We were moving along pretty quickly there. Okay, now there's kind of a famous formula that has a base of e in it, and it's a equals p e to the rt. Where? And I have stars here. If you have a principal or an initial amount that you deposit or you borrow, and there is continuous compounding of the interest, that means little bits of interest over very long periods of time. That means we use a base of e because it's like natural growth. Then the exponent is r times t, where r is the annual interest rate, right? You'll see that as a percent. We'll use it as a decimal. T is the time in years. And then A is the total output amount. So in other words, if you have a starting amount and it grows continuously at a certain rate over a certain time, you'll get an output amount. Okay, so let's see if we can use this formula. I may have to use a separate sheet of paper for more room. Okay, so we're going to use A equals P e to the RT. So what is the total amount for an investment of $500? That's our starting amount, 500. Invested at 4.5%, that's our rate. As a percent or as a decimal, you know to divide by 100. Compounded continuously, that's why we're using a base of E, and our time is 10 years. So let's fill in the formula. They are asking for the total amount, which is A. Our P is 500. Our base of E, and our exponent is R times T, 0.045 times 10. Okay, what we're going to do is just run it through the calculator. Here we go. 500 times E, and the exponent is 0.045 times 10. And because this is money, we'll round it to the nearest cent. $784.16. $784.16. Okay, let's try problem 9A and B using the same formula. Martin borrows $5,500. That's our P. The rate is set at 6%. Okay, they just told us, or 0.06. With continuous compounding, that's our E. How much, that's our amount, does he owe at the end of 2 years? There's our time. There we go. They are asking us for A. They gave us P. There we go. E, continuous compounding. And the exponent is rate times time. Let's run that through the calculator. 5,500. And then E, you can put a multiplication symbol between the 5,500 and the E, or you don't need to. E, and then the exponent is 0.06 times 2. Let's see. That would be $6,201.23. Okay, on B, Martin found a bank with a better interest rate of 5.5%. How much less does he owe at the end of 2 years? So we're going to have the same problem, except the rate is going to be 5.5%. or 0.055 is a decimal instead of 6%. So let's see what he owes if the interest rate is only 5.5% instead of 6. He still borrowed $5,500. Our new rate is 0.055, and it's still for 2 years. Let's go ahead and put this in the calculator. There we go. In this case, he owes $6,139.53. Now, they asked though, how much less does he owe? Notice it says less. So we're going to find the difference between these two dollar amounts in red and blue to find out how much less he has to pay. $6,139.53 minus $6,139.53. He saved himself $61.70 is the final answer. There we go. Did we get everything? Yes, we did. Have a fabulous day.